Now, officially, the unit that we're doing is part of a branch of mathematics that looks at counting, and that branch of mathematics is called combinatorics. So we've done some questions like this already. The first thing that we learned was the spaces, right? Every time you make a decision, you put a space, and then you put the number of choices in each space. So in this one, a new car is being built. You have 3 decisions that need to be made. You need to decide on the color, the transmission, and the interior. Then for color, how many choices do you have? 3. For transmission, how many choices do you have? 2. And for interiors, 2, which makes 12 different vehicles. Now, when you think about actual cars, all the choices that they allow in a car, it can make so many different variations of the same vehicle. Sometimes you'll get a question that will tell you you're allowed to repeat things, and sometimes they'll tell you you're not allowed to repeat things. So if you were using the digits 1 to 7, and you were making a 3-digit number, you would have 3 decisions to make. So both of these would have 3 spaces. If you were not allowed to repeat a number, in other words, it's like this list of numbers are actual physical numbers. Once you pick one of them, it's gone. Well, if I picked one of these numbers to put in the first space, does it make sense that I would have 7 choices? But once I've chosen one of those numbers, if I'm not allowed to repeat, now when I go to grab a second number, I'd have 6 left, and then 5 left after that, which would give me 210. If you were allowed to repeat, in other words, you take the 7 or any number and it's still there as a choice again, you'd still have 7 choices, but then you would have 7 again and then 7 again for 343 choices. So obviously there would be more if you're allowed to repeat compared to not being allowed to repeat. For example 3, we are going to stay with using just the numbers 1 to 7. And we're now going to think about even numbers. And this is something the textbook didn't look at. What would happen if you've got a spaces question where you have decisions to make, but one of the spaces has a restriction on it? Okay? Now don't write this down, but the first way that a person would go about solving this, first time you would look at this question, you'd say, okay, I have 3 decisions. I would have 7 choices here, 6 choices here, and then my question is, what number do you put there? Because it has to be an even number. Now, if we think about 1, 2, 3, 4, 5, 6, 7, does it make sense that the last number has to be either a 2, a 4, or a 6? But the problem with how we've started this right now, when I put a 7 in here, that means I have chosen one of the 7 numbers, but I don't know which one. That 7 doesn't mean you put a 7 there. That 7 means you had 7 choices, and any one of those choices could be there. Which means I could have put a 2 there, but I don't know. I could have put a 4 here, but I don't know. So when I get to my last space, and my last space has to be an even number, I don't know how many options I have left, because I don't know what my choices were to begin with. But to count this same thing, if we deal with the even number first, in other words, we know that the last number has to be either a 2, a 4, or a 6, and we do that restriction first, that would tell us we choose one of those 3 numbers to go there. We have 3 choices. And now, since I either the 2, the 4, or the 6 is gone, how many choices do I have for my first one? 6. And then 5. Giving me 90 ways in total that if I use the digits 1 to 7, and I want to make a 3-digit number that's even, this is the possibility. Now think about this a little bit. Could you still have numbers that start with 2? Could you still have numbers that start with 4? Could you still have numbers that start with 6? Right? Yes. Because basically, this is what we're doing as a tree diagram. As a tree diagram, we dealt with the even number first. So we said, I'm going to look at my last digit. Wow. And it can be a 2, a 4, or a 6. Then the next thing I did was my first digit. If it's a 2, can you see that you would have 6 options? 1, 3, 4, 5, 6, or 7. If it was the 4, you would have 6 options. 1, 2, 3, 5, 6, 7. And if it was the 6, you'd have 6 options. 1, 2, 3, 4, 5, and 7. Then, my second digit, off of each of these, you'd have 5 options, depending on what's left. Right? For this one here, if last one's a 2, first one's a 1, then my second digit can either be a 3, a 4, a 5, a 6, or 7. 5 options. Now, we don't draw tree diagrams for these questions because they take way too much space. Right? In the end, you would have 90 things, 90 branches at the end. But sometimes the tree diagram can help you understand what's going on. Okay? We had to deal with the even number first to make sure we looked at all the options for the restriction. And then the other ones didn't matter, so you just went, there's 6 left, then 5 left. Multiply them together to get 9. Now, in our next question, we're going to do the same thing. I'm still going to use 1 to 7, and I want you to try and figure out how many would be odd. And then once you've figured out how many that could be odd using your strategy, I want you to see if you could think of another strategy to count it the same way. All right. How many people did this as their strategy? Perfect. Makes total sense. We have a restriction. Now it has to be odd. When you are showing your work in this unit with the spaces, if a space has some sort of restriction on it, underneath, just describe that. If you could have written the word odd, I like to list the numbers in this case so that I can count them easy. See that there's 4 options there, 4 choices. And then, now I've used up 1 number. So just because there's a 4 there, that doesn't mean you've used up 4 numbers. That just means you had 4 choices. And you've chosen 1 of those 4. That would leave you with 6 choices there, 5 choices there, 120 in total. But there's also a way that you can use example 2 and example 3 that we just did to figure out example 4. So in example 2, in example 3, we counted how many even ones there are. In example 1, we counted all of them. Another way of counting the odd ones if you had all of them and you subtracted the even ones, what would be left? The odd ones. So if I take all, and this strategy, I actually have a name for this strategy. I call it the not strategy, where you take all and subtract all the ones that are bad. In this case, the bad ones are the even ones. All was 210, even was 90. You would get 120 that way as well. And there will be some questions that we do where it's not easy to count something directly, but it is easy to count the bad ones. So when it's easier to count the bad ones, then we take all of them, subtract the bad ones, and you're left with all the good ones. The unique thing about this unit is that we learn different strategies, but every question is somewhat unique. So you can't just say, oh, I solve it like this because that's how I solve every logarithm equation. Right? Logarithms work that way. You see a log equation, you're supposed to do the same steps every single time, get you the same answer. So sometimes you can memorize how to do something. This unit will cause you to think. Okay? 3-digit numbers. Can you see that this is a decisions question? You would have 3 decisions. Are there any restrictions? Well, you can't repeat. Are there any other restrictions? Good question we have to ask. If we think there are no restrictions, how many choices would I have for the first number? You're saying 9, you're saying 8, 7, 10, okay? There are 10 numbers from 0 to 9. However, if you're making a 3-digit number, is this a 3-digit number? No, that's 17, right? That's how many digits does that one have? 2. Is this a 3-digit number? Or is that still 17? It's still 17. So in this question, there is a restriction on the first digit that this is not 0. That would mean I only have 9 choices for that first decision. If I'm not allowed to repeat, how many choices do you have for your next one? 9 again, because now one of the numbers from 1 to 9 is gone, but 0 gets added back in. And then 2 numbers are gone, giving you 8 after that. Multiply this out, gives you 648. So sometimes it's a little bit tricky to see the restriction. Okay. Other review. Here's some mental math for you. Without a calculator, figure out all 3 of these. And remember, how do you simplify a factorial? You start expanding a bigger one until it cancels out with the one on the bottom. All right, let's check how you did. Did you get 42 for the first one? Because you would expand the bigger one until you got to the 5. The 5s would then simplify, leaving you with 7 times 6, which is 42. The next one, start expanding to 10. You'd have to go 10, 9, 8, 7. I would get to 6. I would cancel out with the 6 factorial on the bottom. Now the 4 factorial is technically 4 times 3 times 2 times 1. Can you see that the 8 would cancel out with the 4 times 2? Okay, and the 9 and the 3, if I keep color coding this, can you see that the 9 and the 3 could cancel out, leaving you with the 3 on top? Now sometimes when you do a lot of canceling, it gets really messy. You might want to take more steps to do this. But now what am I left with? Everything is simplified on the bottom. Can you see that all my numbers are gone on the bottom? On the top, I'm left with a 10, a 7, and then a 3 in orange. 3 times 7 is 21. 21 times 10, 210. So you will find on the non-calculator part of this test maybe some more mental math than you're used to, or bigger numbers. And in C, now we're into algebra. We have to look at the algebra and determine which is bigger, n plus 2 or n. You can put a number in for n if you're having trouble seeing that n plus 2 is bigger. So if I start expanding the bigger one, I'd have n plus 2, then 1 less than that would be n plus 1, and I keep going until 1 less than that would be n until I get to the one on the bottom. And this simplifies to just be n plus 2 times n plus 1. So we've seen this in our notes already. A review. A permutation is when you have a group of objects and you're arranging them and the order matters. Which is first, which is second, which is third. The second part of this unit looks at combinations where the order doesn't matter. So there are places where order matters and places that order doesn't matter. For example, if you're playing a card game where you get 5 cards, some card games you can take those 5 cards and rearrange them in your hand. Other card games, those 5 cards have to stay in the order and you have to play them in the order that you get. Right? Poker, it wouldn't matter what 5 cards, how you got them. You could rearrange them however you like. So there is a place for permutations where the order is important. And there's a place for combinations, which we'll get to later. So combinations will answer like poker hand questions. Permutations answer lots of things like passwords. Can you imagine if someone was able to type the password at the wrong order and still get into your bank account? How, like your PIN. It's super important that your PIN is in the right order. If it wasn't in the right order, they could just like, oh, I picked the right 4 numbers. Doesn't matter which way I type them in, I get into your bank. So, if we had ABC and we wanted to write down all the permutations, ABC, ACB, BAC, BCA, and CAB, CBA. We could write them all down. Now, we could also count this quite quickly with spaces, right? 3 choices for the first one, then 2, then 1, which, of course, is 3 factorial. So the factorial notation comes up a lot in permutations. And we had the formula in our textbook as well. I have it in this notes. The number of permutations. We can remember that the R stood for the spaces. Whatever that number was the number you start with. So if you had 8p2, your formula says this is 8 factorial over 8 minus 2 factorial, which is 8 factorial over 6 factorial. Using spaces, it would say you have 2 spaces, starting with an 8, then a 7, 8 times 7. And you probably can see how the factorial and that are exactly the same. If you had n spaces starting with n, you'd have n minus 1, n minus 2, n minus 3, dot, 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 3, 2, 1. Would it make sense that that would end up being n factorial? Interestingly, though, if you had n spaces using the formula, you get the 0 factorial in the formula. So I don't know if you remember, but when we learned about factorials, I told you that 0 factorial is equal to 1, not because it follows the definition, but we sometimes need it for formulas to work. And this is an example of where that is. Does our school still have a wind ensemble? No. They used to, but not right now. But if they had a wind ensemble that could play 10 pieces of music, right? And we're assuming that if you would go to a concert and they were going to play 4 pieces of music, that they wouldn't play the same 4 times in a row. Usually at a concert, they don't. Have you ever been at a concert where they play the same song twice? Yeah? Like a standing ovation at the end, they're like, we have no more music. Let's just play the second one again. I don't know. But usually you don't play the same song twice. So then, if I had this question, and I was saying how many ways can I solve it, I would realize I have 4 decisions to make. What song is going to be first? What song is second, third, fourth? Does the order matter in a concert? Yes and no, right? What do they like? Concerts like to end with a song that's good, right? You don't want to leave your song that, yeah, this one, nobody liked this song. Let's play it right the last one. So everybody at the end of the concert's kind of like, yeah, right? You also don't want to start with your worst one, so people are like, so you kind of try to hide that one somewhere in the middle of the concert. So the order does matter. Can you see that if there was 10 songs, you would have 10 choices for your first one, right? 9 choices for the second, 8 for the third, then 7, right? And they probably learned "Oh Canada," so they probably wouldn't want to play that one third. It's kind of like awkward, right in the middle of the concert. Okay, I guess we all have to stand up now because they're playing "Oh Canada" right in the middle. But you could also write this as you have 10 objects, placing them in 4 spaces. This would be 10p4. And where this notation is nice is when you have so many spaces you have to write, it's much shorter to do that. Number of permutations in word math. This would just be 4 factorial because you have 4 different letters, right? We have no problems like Mila that we, right? Double E still coming up. So we have no identical objects in math, then it would just be 4 factorial. Okay. So 5 people come in for math help. There are 12 chairs available. How many ways can they be seen? And I find this question in particular, your brain struggles with a little bit. Because it's a spaces question, but your brain will want to make a space for the desks and write 12 spaces, and then put the number of students into the desks, and then run into a problem, because you run out of numbers to put in. But your brain naturally has students put into desks, but this question puts desks into students. Because when you come in, you have to ask yourself, your spaces stand for decisions, they don't stand for desks. How many decisions need to be made? Well, first person walks in, they have a decision. They're going to sit somewhere. Second person walks in, they have a decision. Third, fourth, there would be 5 spaces because 5 people have choices to make. Then, first person can sit anywhere. 12. Okay? How many choices for the next person? 11, right? Because it's very awkward. You come into math help and sit on somebody else's lap. Right? It's like, there's 11 other desks left, and you choose to come sit on my lap. That would be very weird. Okay, so 11, then 10, then 9, then 8. Which is the same as 12. Which is a pretty big number. Again, you have this button on your calculator. You could either type in 12p5, or you could type in 12 times 11 times 10 times 9 times 8 and push enter after that. Now, if we look at this classroom, we have 1, 2, 3, 4, 5, 10, 15, 20, 25, 30, 33 desks. Yes, so 5, 10, 15, 20, 25, 30 plus 3, 33. And in this class, therefore, 8, 12, 16, 19 people. 19 decisions have to be made. If we used any desk anywhere, there would be 19 decisions, 33 choices for the first person, choosing anywhere to sit. How big is this number? I think this is going to be crazy. Go to our calculator. 33. I get 9.96 times 10 to the 25. In fact, this is just an estimation, because those other numbers wouldn't be zeros, but they don't show up on my calculator. Okay? Wow. That is a huge number. That's a crazy big number. I once did it without the empty desks, just with, you know how we change our seating plan each month, the random seating plan generator? I said, just going to use the seating plan that we have right here, which is 19 desks, 19 people. That would be 19 factorial different ways of doing it. And I said, if someone gets the right seating plan perfectly, 100% in the court, you don't have to come back anymore. Just 100%, I'm going to put 100% on your final grade for grade 12 pre-calculus. They're like, okay. The first person, no, they went through it. I probably shouldn't have done this. I was just too tempted. So came up to someone, so it was Mira's turn. She guesses the first one. I'm like, yeah. And every time I was like, yes. Yeah. It goes wrong. You're getting it. It's completely wrong. But I just pretended that it was right. Oh, that's bad, right? I shouldn't have done that. But 19 factorial, even if it's just 19, like, this is a huge number, but 19 factorial, like, that is 1.21 times 10 to the 17. That's crazy hard to guess it right. Even right now, just guessing the first one right, you have a 1 in 19 chance of guessing the first one right. And then even if you guess that one right, then you've got a 1 in 18 of guessing the next one. And a 1 in 17 of the next one. So your chances of getting it right are so, it's possible, but so astronomically small, right, that I could have sent the class at $1 million. And I guarantee you no one would get it. I can't guarantee it. It is possible. But it's so unlikely. Oh. I would like you to change this to match the textbook. I like the textbook's words better. And this is when we looked at, right, people who are problems in this class who have letters that repeat. Right? Double E, double N and double O, right? People whose names have 3 letters but 6 letters, and all sorts of things that we looked at in the last class. So if you have identical objects and you're rearranging them, you first say, well, I have 3 objects in total. That normally would be 3 factorial, but because I have identical G's, I would divide by 2 factorial. For Assisipi, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. Normally that would be 9 factorial, but we have 3 S's, so we're going to have to divide by 3 factorial. We have 2 I's and 2 P's, so we would have to divide out those identical objects to get the total answer. And we found out that there are more ways than just words of having identical objects appear. So this is another strategy in our spaces questions, that when you read a question, you have to say, does this question involve identical objects? So contractors sold model homes of type A, type B, and type C. So you have to ask yourself, are those identical? Because if they are, then it's an identical objects question. If they're not identical, then it's a different kind of question. So in this case, the A's are the same type, the B's are the same type, and the C's are the same type. So how many ways could these houses be arranged on the street? They probably wouldn't want to put all the A's beside each other, all the B's beside each other, all the C's beside each other. But you can see some, if you drive through Winnipeg, you can see some areas where they like only use 2 kinds. And every house is it's either that one or that one, that one or that one, that one or that one, over and over and over again. You can see the same model or style. Of course, some are painted blue and some have got like little different things on them, but they're basically the same house over and over again. How many ways could this be done? Well, this is an identical objects question. If they were all 9 houses differently, it would be 9 factorial. But now we have identical objects. And we have to divide out the identical objects. And we also saw the routes question being an identical objects question. Here's John. He lives 3 blocks north and 6 blocks east of school. So let's draw our city blocks here. John lives north and east of school. So this would be the school, and this would be his home. Yep. Okay. So one way that he could get from school to home would be this path right there. I'll do it in green. Right there. That path in green could be represented as going north, 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 then east, 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 east. As an example. This is an identical objects question because if you rearrange these, they would give you different ones. So the total number of ways would be 9 factorial divided by 6 factorial for the e's, 3 factorial for the n's. And if we actually multiply that out, I think we get 84. I'm going to double check that. That would be good. Or we could also double check that. Remember, by counting the pathways one at a time, anytime you go along a straight pathway, all of these dots, there'd be only one way to all of those. And same thing straight up, there would only be one way. But remember, to get to this dot, you could either get through this one or this one, so then there would be 2. 2 plus 1 is 3, 3 plus 1 is 4, 5, 6, 7, 3, 4, 3 plus 3 is 6, 6 plus 4 is 10. Oops, that's, yeah, 6 plus 4 is 10. Then 10 plus 10, this would be 20. 10 plus 5, 15. 15 plus 6, 21. 21 plus 28. 35. 56. 56 and 28. 84. Works out. So, yeah, there are 84 ways that we could get from school to home. Okay? Now, this method, the identical objects method, is perfect if there's no restrictions. But sometimes we can get this same question where the counting method will be better. For example, here we go. Okay. John is walking home. And for some reason, he always has to go past Beth's house. Okay, now, how many ways can John walk home if he always walks past Beth's house? Well, can you see that he would never, right now, we could take out, right? Hello?
So we have a quick message from the grad committee.
Okay.
Okay, cool, thanks.
So, back to John, walking home, having to walk by Beth's house. So can you also see that this would never happen? You never go to those blocks anymore either. If we were counting it, first of all, we could count how many ways he could get to Beth's house. These would still be 1 and 1 and 1 and 1, 1 and 1, and 2 here, and 1 plus 2, 3, and 2 plus 1, 3, 3 plus 1, 4, 4 plus 1, 5, 3 plus 3, 6, 6 plus 4, 10, and 10 plus 5, 15 ways that he could walk to Beth's house. Now, technically, this dot here would be 15 plus 0, because he's never here. So this would still be 15. And this dot here would be 15 plus 0, still 15. And 15 plus 0, this will still be 15. 15 plus 15, 30. 45 ways now that John can get home and walk by Beth's house. Part C. Something happened, and John is no longer allowed to walk past Beth's house. Court order on his way home. So we could block this point out and count it that way as well, but can someone see a quicker way to count how many ways could John walk home if he is not allowed to walk past Beth's house?
Take the total ways and subtract the.
Yeah, if we took 84 and subtracted the 45, that would leave us with 39 pathways. And those 39, since they're part of the total, and we counted all the ways that were past Beth's house, this is the not strategy of all minus the bad, counting how many ways would be left. Next strategy that was not in our textbook questions is called the grouping strategy. Sometimes you want to count things, but you want to keep certain things together in groups, right? Trying to think, maybe you have a stuffed animal collection still in your room, and you have a shelf where you put them on, and you're like rearranging them, but you would like, oh, I kind of want the pink ones together, and then the black ones together, or maybe you have cats and dogs and elephants. And so you want to keep your cats together, keep your dogs together, keep your elephants together. Then this becomes a grouping question. The way that we solve grouping questions is we first count how many groups you have in total and rearrange those. So with the cats, the dogs, and the elephants, you would have to decide, am I going to put the cats first, the dogs first, or the elephants first? And if you had 3 groups, that would be 3 choices for the first one, 2 choices for the second, 1 choice for the last one, 3 factorial. So we first do however many groups we have, factorial. And then you look in your groups and go, I have 8 cat stuffies. Okay? You totally came in perfect time, right? So you're imagining, we're talking about how you have lots of stuffed animals at your house, and we're rearranging. So you first figure out your groups, and then in each group, you rearrange the ones that are in there. So if you had 8 cat stuffies, you do 8 factorial for cat. And then you have 7 dog stuffies, 7 factorial, and then 482 elephant stuffies, you do 482 factorial. But that's your collection. That's your like. Every time you like, oh, there's a new elephant stuffy. I have to get it. Every single zoo that you go to. Here we go. Now, here's the question I came up with. I'm arranging my math books. I have 4, and these ones can sometimes, like usually in a question, I would put the word different in here, 5 different algebra books, and 4 different geometry books, because sometimes students get a grouping question confused with an identical objects question. Because they're all cat stuffies, are they all the same cat stuffy or are they different? Right? All 482 elephants are different. That's why they're part of your collection. So then you have to, if I'm organizing these books on a shelf, and I want to keep the different subjects, calculus together, algebra together, geometry together, first I do my groups. And I have 3 groups, so that's my first decision that I make. And in that decision, there would be 3 factorial ways of doing how many groups. Then I think about each of my groups separately. If I decided to put my calculus books first, how many choices do I have for arranging those? 4 factorial. Then my algebra books, 5 factorial, and finally my geometry books, 4 factorial. And because these are spaces, you would take the 3 factorial, multiply by the 4 factorial, multiply by the 5 factorial, multiply by the 4 factorial. Get a very big number in the end. This is a springtime question. 5 people, Amy, Bill, Jill, Lee, and Tom, are at the park bench. And they want to sit on that park bench, but Jill and Bill want to sit together. Aww. How many ways can this be done? Well, this is a grouping question because you have two people that want to be grouped together. So if we think of it this way, okay, we've got Jill, Bill, Amy, Lee, and Tom, and these two are grouped together. These ones are all individuals, right? So Jill and Bill can sit together if they're in the middle, they're on the end, but Amy, Lee, and Tom, they don't have to be together. So when we think about, first of all, the number of groups, the answer to this is how many groups are there? There are 4 groups. 1 group of 2 and 3 individuals that are like groups of 1. So we would first say there are 4 factorial ways you can rearrange these. Okay? Sometimes we talk about as groups. Sometimes in this question with just 2 people, right? And maybe you've seen couples like this in the school that like you never see them apart, right? And then you just start to give a name for the entity that was once 2 people but is now 1 person. Just say, that's the Jill Bill. The Jill Bill is going down the hallway. You refer to them in singular because they're now 1 entity that never separates. Right? So then if you were thinking of the Jill Bill as a single person, this is like rearranging 4 people on the park bench because you have Amy, Lee, Tom, and Jill Bill. Okay? Then in a grouping question, you look at each of the individual groups and you say, well, how could any of them be rearranged? Yes, the Jill Bill could be sitting holding left hand, right hand, or right hand, left hand. We are not sure. So they can be arranged in 2 factorial ways. But all the other individuals would just be 1 factorial. So this would be the total. If we multiply this out, we would get 48 in total. Part B. Or 12. Love is in the air, and now they come to the park bench. Jill and Bill and Lee and Amy. Don't worry, Tom gets his revenge in part C. Jill and Bill and Lee and Amy have to sit together. So we've got now Jill and Bill, the Jill Bill, right? And we've got Bill Amy. How many ways can they sit on the park bench if those 2 groups have to sit together? Well, first of all, we do the total number of groups now would be 3 factorial. Right? Tom could be in the middle, Tom could be on the ends, right? And then the Jill Bill group could be Jill, Bill, Bill, Jill, 2 factorial. That looks like 21. Let's try that again. 2 factorial. And the Laney group, 2 factorial, and then Tom. For a total of 6, 2, 24 ways. Part C. Tom's revenge. Something happened. It's surprising. Here, we'll erase this for now. It's surprising that they all still go and sit on this park bench. But now Jill and Bill must not be seated next to each other. Delaney, they're on again, off again. Lee and Amy, they can be together. They can be, they're like fine, no big deal. But whatever happens when we sit on this park bench, Jill and Bill cannot be beside each other. Yeah, like it was bad. Okay? Who knows? Okay? I can see your imagination's just flying right out the screen. Okay, so how do we count this And this is where that not strategy, and especially with the word not in there, is part of the reason why I call it the not strategy, is sometimes it's easier to count what's not something by subtracting the bad ones away from the total. The bad ones would be the Jill bill together, right? We counted that in part A and came up with 48. The all is usually easy to count. 5 people on a park bench. 5 decisions, 5, 4, 3, 2, 1. That would be, all would be 5 factorial. And if we subtracted the bad, we would get 120 minus the 48, leaving us with 72 ways where they're not sitting together. So this is the not strategy. Sometimes it's easier to count all minus the bad.